Hi. Today I will discuss the process of how can we simulate aneurysm based on literature data, which I will use as boundary conditions. So I found this paper published online, study of typical rupture and unruptured aneurysm based on FSI method. I found that the data exists here, which is used as an inlet boundary condition in terms of velocity meters per second, flow velocity, and cardiac cycle. So very simply, I could print screen this graph and I bring it to the software origin lab. You can see here it's a new image, or the other one, delete, not that one. This one is the best way. And then you can see the image is already brought here. It's showing me the x's and y-axis data. So I will set this graph a bit in a good position so I can convert this graph to a table. And then based on that table, I can set it as a transit data for velocity with respect change with time. Here is the x. Here is the data here. I'm trying to do it as much as you can because sometimes it's not easy. Can bring this one actually till here. No, it's actually make it till here. We can choose that number to be 0.85. So the best way when you enlarge this system, you can get more precision on how you can set up your information. So that is the first one. And here's the second point. And you can see every time I move, the data here is changing. So that would be reading for me the x value. So the start point instead of 1 will be 0. And the end point for that is 0.9 based on the graph. And then I come to this one is you can see it's I would say possibly it's not 0 when we can see here maybe it's 0.15. So I'll put 0.15 and then we'll finish 0.85. So now to collect the data, you could use manually pick points, and you can say you go through that chart here and you try to double click, trace the curve nicely, and as much as points you can create or generate, you can definitely get a good outcomes for your graph. So I'll use that point here. Of course, if you get more better graph, you will get even better results. But that's what I found in literature if in case I want to validate my model against to perform some validations to prove my CFD model is working correctly. You can see it's developing the points, and I continue till the waveform finish. And here. So this is usually when you don't have a clinical data and you want to rely on literature data. Of course, you want to cite this data because you would do the validation with it. As soon as you finish from that, you click OK, done. And then very quickly, you generate a table. That is the table generated based on this data. So it's a set of 32 points. Represent the x-axis for me is the time. And this one is the velocity. And time is in seconds based on the graph. And the velocity is meters per second, as you can see it in the graph. Now, if I want to sketch this data to make sure like what I got, it does really represent what I got. So you can see that is technically what we generated from this data. We just duplicated now this to identify it. So we can make that to start from 0. Okay. And then you can see even, let's make that to start. Actually, we can keep it that way. So very nicely, we simply duplicated this graph. I took it from the paper, from the article, and I generated this set of data. And that small number, even we can start it to make sure it starts from 0. You can see we will not change the graph because that number is just there. Right, so that is the first step. Second step, I have a text file is already written. I would just modify it, which is very easy to tidy it up. So this is where I save my files. For case DP, that is transit file. It's called with extension profile, which is the representation for that. So I will Control C that one, and then I will put that somewhere, or I could just resave it again. So this is originally was another file which I generated earlier from different article. And then I will modify that to bring this table. Here, instead of these numbers will be 47, the set of data will be 32. As you can see them from the table here, it's 2 columns, time and velocity. I could copy that one here. And if it doesn't come nicely, I can copy it to Excel sheets and I bring it to that one. So let's try it first here. If it comes really nice, time first it came nicely, no problems, no issues. So that is for me. And file, save as, I will call it BC or 2, such as a second example for me. Okay. And if I go and check that to make sure this is available there, so that is my second data, 32 points, 2 columns, and it's called ANSYS tutorial 1, the name of the file. Close that. That's a simple job is done with this simulation. Now, after I finish my origin lab, I can go to my ANSYS. Ignore what models I'm doing here. I'm doing too much simulations. I will open the mesh. I have the file which for cerebral aneurysm, which is tutorials for the team I'm helping from New York. I'll start the Fluent simulation first to bring the mesh file, and then based on the mesh file, I can set up the boundary conditions. And also I'll show you how to read that text file, which is converted to profile. And as well, how can I change my model to non-Newtonian using the K omega SST turbulence model. So I open that file. Here, import mesh, and when I bring the mesh file, need to locate it first. So I come back here. I remember, I think I saved it somewhere here. It's called FF1 mesh, that one. Okay, and the mesh file is reading for me. It's telling me how many nodes, how many cells, and that's the geometry. It's showed nicely. If I want to display the mesh, later I can do that, or display all of the values, and then we can see what exactly left, and we go through it. Close. Because this geometry is already meshed, so technically I don't need to create a mesh in it. So I will go switch to solutions because I can bring the geometry straightforward to the Fluent. I use that method. It's easy for me to open it nicely with no issues, no drama. Possibly there is another method you're welcome to use, but sometimes I experience some issues. when I open it with Fluent by itself. So now it's reading all the file, and I can see it here. The model is came nicely. Now I can see the edges, display, closed. So that is technically my model. I can resize this to see the mesh and the setup for me, the inlet, but with no values for it. So if I go and check my boundary conditions, I will see what exactly is set. For inlet, for example, it's just telling me there is 0, nothing is set up yet. But part of the things I wanted to use here is the viscous model, which is very important to address if any turbulent K omega 2 equations, and that will be using SST, and then we go through it. Okay, so if that model to be used, you see when I set up the material properties, I change it from fluid called air to blood, and change that value to 1060 kgs per meter cubic. And here it doesn't give me the non-Newtonian options, it's just a constant value. So I'll put just something at this stage, just for example, changing create to create that material properties. But I'll show you how can I set up the non-Newtonian here or activate it. So define models, and then we want to define the viscous, and we ask for turbulence expert. And then from turbulent expert, we will request non-Newtonian, and then say, do you want to activate it? We ask yes. So now when we come to the material properties and we click on the blood, and you can see now it's activated for me, the material property, non-Newtonian material properties. So I have somewhere written these values, so I will just copy them for applying the lambda, the power law index. They're available in the literature. We publish articles about that as well. So lambda is 3.313. N is 0.3568. And mu0 is 0.056. And mu infinity 0.0035. So that will apply for us as a non-Newtonian flow in the system, which is something it's created now, and it's awesome. So after we did that, I'll type here quit to exit the command of define models, and now I want to bring my file. But before you bring that, I need to save the project, because when you save the project, it tells me where this got saved. So it's saved, for example, under the folder DPO and FLTG3, and that's where I need to transfer my transit file boundary conditions so it can be recognized by Fluent. So wait for it to finish, and then I'll do some small things to it. So it's writing the zone map name. Is it finished? I think it did. Usually it tells me. Before that, let's as well. I also like to convert the mesh to polyhedra. So I want to convert that. So set up conversion to polyhedron mesh. So let's wait for it as well. Be a nice mesh with polyhedra. The purpose of using polyhedra, the results will be still acceptable, no issues. However, they will reduce the time simulation and make it really faster, especially for this recorded video. So optimizing polyhedra mesh. All right, so it's done. Display, you can see the mesh is changed to polyhedral. Awesome. So now, since I've done that, that's what I was saying. It's a cell count is giving me the total and all the specification I need to know about my mesh quality, which is showing reasonable good numbers, good outcomes. But the most important for me, I need to determine the location of this folder so I can put my transit table there because that what Fluent can read it. So I come here, DP, and then search for FL. I would just refresh that because it's created new folder here. But before that, actually, I needed to copy this folder and then come to Fluent, and then that is the workflow. You bring that transit file here. I'll put this folder on the side because I may need to get some information from it. And now we will start setting up or learn how to read it. So enter, and then we type file, and then read transient table. It possibly will not be accepted because or at first stage. So I need to as well go back to my model and change this to from steady to transit analysis. But now let's see if it will pick up for me. So the name of the file will be called. So I will copy exactly what was transient. So I'm copying with the extension. That way we'll see. So it's reading for me, saying reading transient profile, and it's giving me the values for it. So that's a good sign. I'll go to my general model to make sure I'm doing transit analysis and as well gravity. And you can see based on the model, we could set up the gravity in the negative minus y minus 9.81 meters per second square. And then when we came to inlet properties, or the boundary conditions, I prefer to go there. Inlet, choose the profile. You can see my ANSYS tutorial is time and velocity there. And it's showing me that I have the 32 points, which is a good, and it's already there. So edit that file. And I came instead of that, I will select ANSYS tutorial velocity and apply and then close. That way, I like guarantee that I can read this file correctly in the system. Now, outlet boundary conditions, we could use 0 or some constant values. So I'll put like around 12,000 Pascal as a constant value for all outlets. But if you have a pressure waveforms, that's good. We could convert it the same way and we could add another table and for that value. So it's again, I'm showing you one method and you can adopt and try other methods, which is very useful. You go through it. Close. At the wall, here we check it is no slip boundary condition, stationary wall, rigid wall, and everything is fine. So close, I'm not changing anything there. We also, every time I finish a steps, I try to save the project to make sure everything is going nicely and smoothly. Right, still reading. It's writing all the files. Sometimes when I open Zoom, it's just long from the processor from the computer. When I'm recording, it's fine. Wait a few seconds. Right, so it's finished that side of the simulation. Let's see if I'm sharing the screen. Okay, cool. It just took a bit of time, but it should be fine. Now, after finishing this step, we could go and initialize, but before initialize, let's check mesh interface. We don't have there something to add, methods. Method use simple, second order. Yeah, I'll keep it at this stage. Control, yeah, keep it the same, not changing much. Definitions. Residual, some people recommend that to be added to the 10 to the power minus 5. So I would do that as well. Okay. And reports, we could find the new. So surface report, which is we can find the area or the flow rate at the inlet. Okay. And then we can find another surface report, flow rate at one of the outlets. So let's choose outlet 3. Okay. And then let's try to find something about volume report, volume average, the pressure. We report that, see how the pressure is responding. And when we come to initializations, you can see if I select the inlet, it will bring me the velocity, which we already start with X value and finding it. But if we want to perform some hybrid initialization, we can do that as well. Just to check the system is working. Good. Hybrid initialization is done. Then we need to set some of activities under calculation section. Waiting just the computer to finish. Yes, type of simulations, I will be very patient with that to not stress the computer. Here for calculation activities, solution data to export. So the first thing, I'll export data for the CAT CFD post. I'll choose inlet and outlet, pressure, velocity, all of these sets. And as well, I'll choose washy stress, maybe Y star and Y plus, anything else if you're interested. Browse, that's a place where everything will be saved. You can see my boundary condition transit results table, and that should be okay. And then I want to create solution data export, which we recommend is for creating a MATLAB script for the wall shear stress parameters. So the wall only you choose and deselect the following because I don't need them. I just need the Washy stress. So based on the Washy stress X, Y, and Z, we could generate the time average Washy stress, RRT, OSI, ECAP, and other parameters important or they are derivatives for Washy stress. Okay, same place here, that's fine. All right, we come to run calculations. We choose this like about 0.01. It's a 100 number of time steps, so 100 times 0.01, that will give me a solution for 1 second. And then maximum iteration, I'll reduce that just to make my simulation faster, just for the purpose of recording, and everything is fine. Then I'll say calculate. So I will start few steps to show you how it looks when performs the calculations, and then I will pause the video and come back to it when it's finishing the calculation so I can show you some post-processing of the results. So after a while of waiting for the simulation, you can see now it's reached almost 99% of the simulation. So you can see the residuals as reaching to the convergence. And as I mentioned before, I set it up 10 to the power 1 to the power minus 5. And this is representing for me the flow rate with respect to pressure. Yeah, so I'll leave the model just to close and save everything. And then we go and test and see some of the results for this analysis. Right, so calculation is complete. We can check, here's the flow rate of pressure for the volume. It's created a reasonable pressure, but we will investigate that and see what's going on. Here's the flow rate of pressure, and this one is volume average of pressure. I want to check the velocity, but because I selected pressure, but that's what we do in the post-processing. So at the same time, we could check some of the graphics solutions, contours, and we can select here is the turbulence. I'm interested to check the Y plus, wall Y plus for the wall. And let's see, save and display. What is the value for it? So it's reached to the value, maximum value. If you remove the global and save it is 1.1. So that is really good. It's below than 2. We can make it general. And that's a reasonable and good simulation for this type of geometry, which is very good. Also, we could check the mesh display. Looks really also good. And we could also check the wall shear stress, and that will be showing like there's a maximum value somewhere about 81.56, but actually we can go and explore this in more details in the workbench post-processing. So what I usually as well make sure that here is the file saved for us. I will save this, first close this one and save it to make sure I don't lose my the analysis we done, so I can read them, the post-processing, and come to them. Right, so you see here is the model and everything set up. Now I'll bring the results to show you how can we see more other important information and see how is this working with respect to time. So to read the data file generated, so load results, I usually save the direction of the file where I saved everything. You can see this is reading for me the 100 case files from 0 to 100, and then the other files which could be used as a text. So I will read the first one, and then that will bring to me everything. It would take a bit of time to read these files. And then when you come here, you can see that's the time from 0.01 to 1 second. You can process the geometry. Let's make it something 0.7 as an example, transparency. So it's nicely, we can see anything inside. What I like to do as well is just to take some plans in the geometry. I think we are somewhere around this point, minus 100. Let's see, minus 100. You can see that's a good location, reasonable location. So I want to see what is developed in the velocity. If I want to know where is my inlet, I could highlight it. So I'm choosing something close to my inlet. If I want to go and move down, maybe let's try 110. See if it goes, oh, went up. So minus 90. Yeah, better if I knew my geometry, I could minus 100. then it's very sensitive. It's very, okay, it's very small. So the range is obviously from minus 105.7 to 89. So that's the range of it, you can see. So if I choose any values between them, you can see how can I go from a very quick value, so possibly minus 99, and then because this is very small, so that's a good location. Usually I just remove that, make it to face that direction, and then I could select some points. Another point. Another point. Okay. But also these points, if you can see them now when I shoot them, those are the points I selected them on that plane. But I could also investigate some contours or different things, like for example, pressure, local. But instead of using it for the entire inlet or outlet, I could use that plan to show my results, and I could change that with respect to changing the time, which I predict based on the original velocity. You can see the maximum is around this point. So based on the table, the maximum velocity, it's with the time point, so 67.78, 0.799, so it's about 0.19, so it's about 0.2. So if we see this 0.2 here, you should get the maximum velocity or maximum pressure values, which is the systolic. But that could be difference in the pressure, and that's required some more investigation through it. We could play with a legend to make this appearance as nicely as a fixed, and then that will show you the pressure distribution. And if we don't want to do that with respect to pressure, we can do the same thing with respect to velocity. And you can see how the velocity distribution from the inlet and going through the aneurysm. Also another option we could choose is to select the vector, and the vector will be as well on plane 1. And when you use vector, just deselect the plane so you can see the results, and then you can see the changes of that vector with respect to time. So what I usually do, bring that one highlighted nicely so people can imagine what's going on there. And at the same time, I could use that to be at this time 0.01. It takes a bit of time. And then we can generate a nice video on how this will change with respect to time. I click on this option and then make sure save the movie. I'll browse that movie to be saved somewhere easy to access, which will be the case file, the DP, FLTG. Yeah, that's could be a good one, good place. I will say save, and then I'll play that. To play that will take about really a good time. Current time step is 1, so I'll pause the video, and when it's finished, I'll come back. All right, so after running this, we got the following video, which you can see how the velocity flow vectors go through that plane for the time from 0 to 1 second. And that's showing as well like the nature of the pulsatile flow during the system. So the model looks like it's working. There's no big issues. Another things we could investigate is actually those points I selected. But before that, we could as well plot another contour to represent the wall shear stress. So instead of the inlet, we select the wall artery, instead of the pressure, we could select the wall shear and make it local, and then we can see the values for it. So this one is definitely for 1 second. If we go to the maximum, as we say, it's close to 0.2, you can see that it could give me the values. 0.2 is trying to reach to that time. Since this is not giving me much of information, I could really play with the range, use specific value. So use 0. Maybe 2 and see how it looks. Yeah, looks reasonable. Distribution, I could change that to keep it smooth, but remove the different parameters, and as well change the transparency. If you make it 1, would be really like that. It's not really good, but 0.2, it will give it nice color, and you can as well deactivate the vector and anything to not impact on the model. If that is not what you want, you can change the transparency to something, to 0, and you can go through it. If you don't want to show the contour, then you just remove it, and then you can produce nice images for your publications. Definitely you can repeat that for different times iterations. So I moved to 0.3 seconds, and I will check how this will change with respect to the time. And you can see how the model is respond to it. Something else we could investigate is plotting. As you remember, I selected 3 points, so I come to XY plot and use the X transit. We have 3 points, so that will be 0.1, and then I select 0.2, and I select 0.3, X, Y. Instead of pressure, we could choose and investigate the velocity. This will be the magnitude, the absolute value of the velocity, so it's not really as represented, so all the positive numbers, and you see that. So this type of calculations will take a bit of time, so I will pause the video and come back to it to show you the outcomes for this. So yeah, after running these results, you can see clearly the velocity profiles for the 3 points which I identified earlier, 0.1, 0.2, 0.3, and you can see how the velocity respond with change of the time, and you can see there is a time shift, time shift between them, which is something good to see in this type of models. So definitely the model is working, and I can see really good outcomes from it. Maybe the next video I'll record, like future, with help some of colleagues, like how to plot time average washes stress and RRT for the exported result for the washes stress. Thank you very much. I hope you find this video is helpful.